You have 2 apples, and you get 3 more apples. How many apples do you have? This seemingly straightforward question can be challenging for language models, even if trained at scale. However, we would want generic language models to possess some mathematical abilities. Here, we scrutinize one commonly used language model, BERT, whether it has some mathematical skills, and if so, to what degree. We measure that by fine-tuning it on a popular math word problems dataset, Aquarat. The model receives input question and possible answers, and has to choose the correct one. We hypothesize that we can improve mathematics in language models by self-supervised training on explanations of how the solutions were derived, so-called rationals. We also suggest a new loss for better utilization of the rationals. Rationals are a step-by-step derivation of the solution. We use them for self-supervised training and then discard them for fine-tuning. They might contain both natural language, formal mathematics, and anything in between. Therefore, they can be looked at as a bridge for the natural language model to learn formal mathematics. For better utilization of the rationals, we suggest another loss. We call it neighbor reasoning order prediction, NROP. NROP is a coherence loss that forces the model to pay greater attention to rational. We split the reasoning into steps, and then for 50% of data points, we randomly swap 2 neighboring steps. We combine NROP loss with standard MLM loss. To measure the impact of the rationals and our loss, we conduct 4 experiments. BERT base, directly fine-tuned BERTs to predict the correct answer. BERT Aqua, which is a BERT with additional MLM training only on questions. BERT Aquarat, BERT with additional MLM training on questions combined with rationals. And BERT NROP, BERT with additional MLM and NROP training on questions combined with rationals. In all our experiments, rationals were used only for additional self-supervised training. BERT with additional NROP training achieves state-of-the-art results across the models with low inductive biases, and even on par with more tailored models. The results also show that both our hypotheses hold. Rationals improved the results, and NROP improved it even further. However, one could argue that BERT Aquarat with training on rationals was better than BERT Aqua, simply because the model had access to more data. To make a fair comparison between the 2 models, we first measured that rationals contain, on average, around 2 times more tokens than questions. Therefore, we need 3 times more data points for BERT Aqua than for BERT Aquarat. We created pairs of samples with rationals and without rationals with similar numbers of tokens and compared the score. The results show that rational tokens were utilized much better than question tokens, and that they are indeed qualitatively better for learning mathematical skills. Further investigation of the models revealed other observations. First of all, BERT's embeddings, even after fine-tuning to predict the correct answer, had no information about basic operators. Interestingly, BERT NROP seems to retrieve some information about them. We wanted to look at specific examples of what questions does BERT solve and what he does not. However, random guessing on Aquarat yields 20% accuracy, which would make it hard to distinguish solved questions from pure luck. With that in mind, we have constructed a new evaluation task, the permutation consistency test. Each question is copied 5 times with the correct answer at a different position. Model scores 1 point only if it solves all 5 questions. Therefore, the random chance in this experiment is lower than 1/10 of a percentile. In this test, our model solved 3 times as many questions as BERT. Additionally, we found that in most of the questions solved by BERT, answer was either round or in another way different than the other candidates. We did not find a similar pattern in questions solved by BERT NROP. Results of the permutation consistency test also suggest that models rely strongly on the order of the answers. To reduce such bias, we test several permutation variant losses. For those who are interested, details can be found in the paper. To better understand the model's performance, we check which questions are difficult for the model. We categorize questions by their difficulty for BERT NROP and BERT. To estimate a question's difficulty, we have ranked the candidate answers according to the model's uncertainties. For instance, if the correct answer has the second largest probability, we assign to that question difficulty 2. With that method, we group questions into 5 difficulty categories, from the easiest D1 to the hardest D5. Manual inspection shows that for BERT NROP, these groups show somewhat expected patterns ranging from single operations to number theory problems or those that require additional knowledge. We did not observe a similar pattern for BERT, except the easiest group, where the model chooses the answer that is somewhat different from the other candidates. To confirm our observations about the difficulty, we conducted a human study, but for that and more details, we encourage you to check out the paper.